And hello, welcome YouTube to this video. So in the last videos, we've been talking about steady-state simulations with heat exchangers and the like. However, we have not touched on the dynamic simulation capabilities of DWSim. So I want to introduce that to you. You will be able to find resources online on how this is done, especially with the tutorial available in the help. So let me close all of this. Yeah, so this is the DWSim you're normally used to, and I've set up some flow sheet here. And don't worry, I will guide you through the steps through doing it. But let me first show you where the tutorial is for the controller, dynamic simulation. So if you're not sure, you can always go to the help tab, go to documentation, and you'll see this thing called user guide. Once you see this user guide, you can open it up, and you will likely open up to like Internet Explorer, or more likely Microsoft Edge, right? Microsoft Edge. Okay, and this is DWSim. Okay, so you can look through the contents. So scroll all the way down to the bottom, and you will be able to see some tutorials. So scroll, and then you see this thing called how-to tutorials, right? How-to tutorials. Okay, this will show you some of the interesting, setups for various things, like this steam methane reforming tutorial. You can go and check out what you need to do. Like for catalytic reactions, you can solve this. Okay, you can but you keep scrolling down, or if you want, go to contents and you go to how-to tutorials, go into this thing called basic dynamic simulation tutorial. So this is one of the more advanced stuff, but I'm skipping ahead a lot of the I'm skipping ahead because I'm not involved with distillation and stuff at this point. There are lots of tutorials already online for that. I might make one if it's needed, but if it's needed for myself, but I'm not going to use it now. So my interest is more on HVAC, right? Heating, ventilation, air conditioning, or refrigeration, heating and cooling, basically. It's a heat transfer studies. So what you need to do, you can follow this tutorial. It says you will use water as the only compound and use steam table property package. So that's if you want to follow the tutorial. You can follow step by step using the user guide. I'm going to do a slightly different version of this tutorial, and I'm going to use, instead of water, I'm going to use terminal. Okay, I'm going to use terminal, and just to let you know what steps I took, I'm going to delete all of this and start from the beginning. Okay, so I'm going to delete. I'm going to turn dynamic mode off, delete tank, delete this thing. Okay, delete. Okay, and all that will be left is a material stream called terminal stream inlet. Okay, we'll just give it a pressure of 180,000 Pascal. Okay, why is it so? You may find out later on. Okay, so we'll make this stream go through a valve. Okay, we'll make this stream go through a valve just like the tutorial. You'll have a terminal stream inlet, and the outlet is here. Yeah, one thing of note for this valve is that you must for dynamic simulation, we should be using this general service KV. Okay, KV valve, meaning to say, well, where does this K come from? If you remember Bernoulli equation, okay, and we can just go to this Princeton EDU site, whatever this is. Okay, this Bernoulli's equation is usually the equation of conservation of mechanical energy. Very familiar equation. I'm not going to go through that again, but you know that friction losses are somehow correlated to the the dynamic pressure of the fluid, which is half rho v square. Half rho v square is like the dynamic pressure. Okay. So yeah, your rate of coefficient of loss, or rather your loss term, is actually correlated to the half rho v square via some k values, and that's what the kv here is. I assume you know that, so I won't be going through that again. Okay. So yeah, you can specify the pressure drop of the valve using a kV. The kV will automatically calculate pressure drops based on the flow rate of the fluid. And then yeah, so if you do the soft flow sheet, we will see that this this what do you call that? This pressure drops around 10,000 pascals. All right. And what you can do also basically is you should also set the use opening percent versus kV max relationship. What does this mean? Well, you know, in a valve you can actually I guess turn a knob or something, and if you turn the knob one way, the flow rate will become greater, just like in your bathroom tap. If you turn the knob the other way, the flow will become smaller. So what does this mean? It means that if you turn the knob one way, the resistance to flow becomes greater. You turn the knob the other way, the resistance to flow becomes smaller. And that is what this valve opening percentage is about over here, right? This is what the valve percent here is about. And based on the valve percent, you know, if it's open, you have a lower kV. If it's closed fully, you have the maximum kV. So kV is the friction coefficient of the valve, and of course it's variable based on how much percent of the valve is open. So if it's fully open, we do not experience any pressure drop. Okay, so I don't know why this isn't getting some sort of pressure drop. Okay, so let's see. Say valve capacity too small, increase kV. Okay, maybe 10, 50. Okay, so yeah, I think that there's something to be mentioned about having your valve opening too small, too big, whatever it is. But I'm going to leave that discussion for next time. And as of now, I'm not too clear myself why it's popping out all those errors as I play around with the values. But yeah, for the first yeah, if I get the answers, then maybe I'll present them in another video. And as I say, yeah, this video series is, you know, as I learn, I make videos. So I know a little bit, and whatever I know, I'll just present to enhance my own memory and learning experience. But also, hopefully, if you're lost like me at first, you can go through the path I just went through. Yeah. I hope it's of help to you. It may or may not be. Okay, no promises. Okay, but anyway, so yeah, let's keep going. Yeah, the valve is now 50% open. Okay, 50% open, and it drops from 180,000 pascals to 130,000 pascals. So that's what we are having here. Okay, now next thing I need to bring you is the tank. Okay, tanks will be under the separator / tank column or tab. You can just drag one out here. Okay, the standard tutorial tank volume, you just put 2 meter cube, and that is enough. So we can connect the inlet stream MSTR02 and we make an outlet stream MSTR03. So this is tank 01. And then of course we'll get another valve which is under pressure changes. Okay, valve 02, you can also give it a general service kV. Okay, make sure you check the kV to kV max is, or kV max is 400. That is what is stated in the tutorial. and then use a valve opening versus kV max relationship. Leave the valve opening percentage as 50%, and then bring in MSTR03, and we will make an exit here. Okay, we'll make an exit here. So that's how you set up your steady state thing. All right. So this is a very easy setup of a steady state. We have a 2 meter cube tank volume, a terminal stream, a valve, MSTR02, a tank, another stream coming out, MSTR03, flowing through valve 02, and finally MSTR04, 32.9. Okay, some of these values will change because it's a dynamic simulation, and yeah, so that's what we have. Now, so let's highlight some steps. Okay, we made a steady state simulation. And to transition it into a dynamic simulation, we will need to make a few changes. So do pay attention right now. Okay, it's 11:20, 11 minutes 20 seconds. So yeah, do pay attention. So we make a steady state simulation. Now let's make the dynamic simulation. All right. So what we need to do is ensure there are a few things we need to pay attention to. Make sure your valves are in general service KV mode or whatever KV mode that you have in maybe future versions. Make sure you have a tank, and also one thing for sure, pipes actually don't work with dynamic simulation. So if I do a pipe here, I give an inlet, outlet, and energy stream. Okay. I'll give you MSTR05. Okay. Of course, we just specify some random hydraulic profile. PVC length 1, 0.1, 1 inch. Click check OK. And you should be able to solve the flow sheet. Yeah, it's very simple to solve the pipe. Alright, so one thing I want to demonstrate is that pipes are not ready for dynamic simulation yet. So the way to activate dynamic simulation mode, you go to the solve flow sheet button here, which is on the top tab just below dashboard. Okay, but just go to the right a little bit, and then you see this thing called dynamics. Okay, there'll be dynamic mode active, inactive, dynamics manager, and integrator controls. Now that's a lot of things to go through, but let's just start with the first step. How do we turn on dynamic mode? So you see this run thing, dynamic mode active, inactive. Just click that thing. Okay, and once we click that thing, we will see a few things here. We will see this flow rate with a F over here. We will see this material stream with a P on top, and we will see this pipe with a exclamation mark on top. What does this exclamation mark mean? Well, if you take a look at the user guide, you go to this part called, okay, here, yeah, you can find it in the user guide. I'm not gonna search it out. But what it says here, if it has this exclamation mark, it means it's not supported by dynamic mode. So you cannot use pipes for dynamic mode, unfortunately. You might need to program some things in yourself. So I'm going to delete the pipe off. So out of the box, you cannot use pipes in dynamic mode. You probably have to program something in. Okay, but this is kind of beyond the scope of these videos. This is just the basic. The idea is to get you started. Very basic steps. Okay, so to turn dynamic mode on, very simple. We just turn on this dynamic mode active, inactive. And then how do we do a dynamic mode simulation? Okay, so the way to manage your dynamic mode simulation is to go to this dynamics manager. Okay, so I'm going to delete all of this. Because when you start, you will not have anything really new there. Okay, you will not have anything there. Okay, all you will have is this screen. And there are a few things you should check. All endpoint material streams are connected to control valves. So see, endpoint material streams, they are connected to control valves. Okay, that's one. Okay, and the second way you can access Dynamic Manager is through the tab on top here, Flowsheet Dynamics Manager. Some of these may or may not be here, but you can always click this Dynamics Manager, you will get there anyway. Alright, so there are lots of things here. Okay, so where do you start? Okay, so the way to think about dynamic simulation is assume like you're solving an ODE. Alright, I assume you know what an ODE is, how to solve them using numerical methods, because I won't be going through that in this video. Do search out some videos on how to solve ODEs and boundary value problems by yourself. Please take note how it's done. Only with that prerequisite knowledge can you understand what I'm talking about in this video. Alright, so for ODEs, there are a few things you need. Okay, you need initial values. Okay, so the initial values are basically what you specify here, and this will become so-called initial conditions for this ODE. Right? You need initial values, you need boundary values. So at the boundary of the flow, there should be something that is fixed. So that's what this F and P are for. They specify what is fixed as the boundary value. Now, what am I talking about? Well, and how do you change this F and this P? Because when you start your flow sheet, you might have this letter P on top. Okay, to change this F and P, you need to go to the tabs under Dynamics. Your dynamic spec, you either have to select pressure or flow. So if I select pressure, it will turn to a P. If I select flow, it will turn to an F. So F means I specify the flow rate. It means that at this boundary on the left, flow rate is fixed. At this boundary on the right, pressure is fixed. Now you need to have all your flow streams at the boundary of your problem. So for example, here is the left boundary of this thing, because this inlet stream is going into valve 1, but it seems to be coming out of nowhere. So this is your left boundary. This right stream is the material stream exiting the system, so this is also a boundary. You need to make sure those boundaries are fixed. Now I also said you need an initial value. Okay, how do you set the initial value? Alright, okay, so the way to sort of save initial values is to go to the flowsheet states. So flowsheet states are just to the right of your dynamic mode active inactive part. Okay, you will see this thing called flowsheet states. Now when you start, there won't be any flowsheet state available. Okay, so what you have to do is okay, I'm just going to delete the ones I saved. Okay, what you have to do is to you have to set some flowsheet states. Okay, you have to set some flowsheet states, and you have to you have to set some flowsheet states, and what you need to do is save them. Okay, so flowsheet states represents the initial value of the equation, so to speak. So what you see here in the steady state solution are the initial values. Okay, you can set for each material stream. So over here the initial values will be 32.6 degrees C, 180,000 Pascal, 36,000 kg per hour, which is 10 kg per second. Okay, and all of these things you see here will be these initial values. So let's set the initial values one at a time. Okay, at the terminal stream inlet, you can set the temperature, pressure, and mass flow rate. The valve doesn't need any initial values because we fixed it already. This one, MSTR02, we will not touch anything because all the initial values will be determined by this flow rate upstream and the valve. For the tank, you need to set some initial values. So for the tank, what you need to set is One of course is your tank volume. That's your calculation parameters. And by the tank volume, you will be able to kind of see the fluid residence time. Okay, I will not go through how to calculate that. That's very basic. I assume you know. That's prerequisite knowledge. Residence time. Okay, what other initial values we need to set? We can set the liquid level. Here is initial value of 0 meters. We can set the available liquid height. So what is the height of this tank? Okay, because in steady state mode, you will only set the tank volume. You will not be able to set the rest of the tank dimensions. However, in dynamic mode, you will be able to set the maximum height of the tank. And assuming the tank is cylindrical, you will be able to sort of guess or calculate the diameter as well. Okay, this one says initialize using inlet. It says here what? Initialize tank's content with information from the inlet stream if the vessel content is null. So you can choose to initialize the tank content from the inlet, and this will of course give you an initial condition. I'm not going to switch that on because that is not required in your tutorial. Okay, so the only thing for the tank is to set volume to 2 meter cube, available liquid height to 2 meter, and set the reset content property to 1. What is this reset content property? It's over here. It says empties the tank's content on next run. So that means every time you run the simulation, okay, every time you run a simulation, the tank will be empty, and that will be your initial condition. So we will set that to 1, since that's what the tutorial says. Yeah, and this one we will not set anything, any initial condition. We'll just leave it as it is. The valve O2, we will not set any initial condition. But over here at the exit, we do want to set something because well, in the tutorial we will have the flow exit to atmospheric pressure. Why is that important? Is because, yeah, I mean, if you're having flow exposed to air, I mean the pressure will be atmospheric. Okay, that is the logical thing. But anyway, that's what the tutorial is. So we will just set this initial condition to 1 atmosphere, and that will be the fixed value of pressure at this end of the tank, or at the end of the exit stream. Okay. Now once we sort of deal with all the initial values and we are satisfied, we can actually save the flowsheet state, and this will be a set of initial values that we will use for our calculation. So go to flowsheet states, just to the right of dynamics, and then you just you can save. You can say this is called state 1. Okay, you can call this state 1, and yeah, you can save this set of initial conditions here. Now this is sort of optional for you. I don't think it's strictly necessary for dynamic simulation, but it is useful in case you want to save a set of initial conditions. Okay, next thing, so we set our boundary conditions and our initial conditions, right? What then do we need to do next? So there are a few things we need to do. One is, well, you just ignore all these tabs here. We'll go for the simplest bare bones simulation. Okay, so the other thing is that we need to determine, okay, if we were to solve ODE problem or PDE problem, partial differential equation problem. Yeah, if we need to solve that, we need boundary conditions, we need initial conditions. We also need a way of discretizing the equation and solving the equation. So that's a lot of big words. If you're familiar with simulation, then yeah, okay, you'll know what I'm talking about. If not, then yeah, well, let's go back to numerical solutions of ODE. numerical solutions of ODE, we will kind of need to break down that dy dx or dy dt into some sort of approximation. Okay, maybe y2 minus y1 over delta t or something like that. And then that's how you kind of discretize your equations. And then yeah, so you will need to decide your delta t, which is your time step. You will need to decide how long you want to integrate it for. And all of these settings you will find under the integrator part. And that's it. Okay, so this is the last minimum thing you need. So the first thing here is this integration step, which is in milliseconds. So your basic tutorial will just say 5 seconds, which is 5000 milliseconds. So we'll just leave it be. Duration, we'll see this thing here. You may see this thing here called 10 AM. Okay, something is obviously wrong here. It is the number format, which is in a date and time rather than, you know, just 10 minutes. Why is it 12:10 AM? Why is this 10 minutes? Because 12 AM is 0 hour, 0 minutes, and 0 seconds. So if you want 10 minutes, right? The way to represent is 0 hours, 10 minutes, 0 seconds. So if you convert that to a time format, that will be literally 12:10 AM. And that's what you are seeing here. So don't be alarmed that this thing is 12:10 AM. It just means there's a number formatting error in this thing. But yeah, what you're seeing here literally represents 10 minutes. Okay, so what's this thing here called real-time integration step? Okay, real-time integration step means if you were to ever select real-time mode, that means you want to pretend the simulation is running in real time. Then you integrate, right? Or rather you set a time step that's not equal to 5 seconds, maybe 1 second. But don't worry about real-time integration step. First, we will just leave this part as a default. Calculation rates, everything here we'll leave as default. So pretty much we'll just leave all the properties here as default. But the two things you might want to take note of are the integration step here and the duration. Okay, duration is how long do you want to how much simulation time do you want to do your simulation for. Alright, so we have 10 minutes of simulation time in this case with a time step of 5 seconds. Okay, monitored variables, well, we'll see whether we need to do this. In the tutorial, we are told to specify a few monitored variables, but for now, we are not going to do any of that. We'll see whether it works. Alright, so what have we done so far? We have set our boundary values. We have fixed our boundary conditions. We have set our initial values by going through each of the components. And then we also set our integrator, which will set our time step and how long you want to do our simulation for. Now we are pretty much ready to run our simulation. So what do we need to do? Okay, so to tie everything together, we use this thing called the schedules tab. Okay, schedules tab is basically what manages the whole solver. Okay, meaning to say what is your boundary value, what is your initial value, and then what are your boundary values and what are your initial values. Okay, and what's your integrator, meaning to say what's your time step. Alright, so associated integrator talks about time steps, so you have to actually save your settings under one of these integrators. So you need to save these settings first, or else you'll have nothing to select here from the drop down menu. So go to integrators and select the new one. We'll call this name default integrator or default int. Okay, so default int will be literally all your default values. Nothing special here. So we'll just select this default integrator, and of course we will need to we will need to select which flowsheet state we need. So flowsheet states will provide all our boundary value and initial values as well. So we can select state 1, which we saved just now,
Okay, if you don't want that, we can just use the current state instead, which means to say whatever state our flow sheet is in, we will just use this as our initial and boundary value. Okay, for starters, we may not need to use this initial flow sheet state, so we are just going to leave that up for the time being, and maybe next time we will, if we need to load the same state again, we will use that. If we want to use that same set of boundary conditions and initial conditions again, then we will use this flow sheet state. Now, so all our settings and everything will be set under schedules. Okay, under schedules. So under schedules, you have this thing called event list and cause and effect matrix, and reset empty contents of all volume defined objects before running. All of these things, don't worry about it first. We will not discuss it in this video. The only things we need to pay attention to for beginners, associated integrator, and initial flowsheet state. So these are the things we need to pay attention to. So again, just like integrators, we need to save our settings. For schedules, we also need to save our settings. So is maybe we'll call this test SCH1, test schedule 1. Okay, and that's how we save our integration settings. Okay, yeah, we will save it like so, and that's it. Okay, so test SCH1, you should make sure that the associated integrator is default int. Initial flowsheet state, we'll just call it use the current state. Right, use the current state. Okay, so now we are pretty much ready to start our simulation, if I'm not wrong. So how do we start the simulation? So remember, we saved our settings under the Dynamics Manager, under integrators and schedules. So remember, we need to save our settings under integrators and save our settings under schedules. So to run the thing, we will use the thing called integrator controls. So dynamics, remember, we have 3 tabs, 3 buttons. One is dynamic mode active inactive, one is Dynamics Manager, one is integrator controls. So to start our simulation, we use integrator controls, and under integrator controls, we will have a few buttons we can play with here. So we can see that under schedule, we will have test schedule 1, which is what we saved under schedules just now. So unless you have to save your settings under a file name using this plus button. Of course, you can use the X button to delete it, but you have to save it here in order for it to appear here, right? So this is how you do it, and if you press run schedule, you should be able to get things done. Okay, so well, what do we have here? It says nullable object must have value. Okay, yeah, something is wrong, but it appears that after I restart it a few times, it seems to work pretty okay. Okay, so you can see that our flow rate is the thing seems to work. Yeah, so sometimes there will be errors that, like what we have just now. The most common debugging step is to restart the simulation. So that's what, when I run into an error, I just restart the thing. Okay, so as you can see, when I restart the simulation, it is pretty much okay, and we are hovering around a steady state of 36,000 kg per hour in, 36,000 kg per hour out. Alright, so yeah, and then we can check the tank liquid level. The liquid level, as you can barely see here, 0.29 something something. It's a little bit hard to see, which is sometimes why it's a good idea to give an indicator. Alright, so that's the last thing I want to talk about this video before I end. So under indicators, we can go to this thing called level gauge. So you can just drag it out here. And under this gauge, we can monitor an object and a property of that object.
So what's the object we want to monitor? It's our tank. And then the property we want to measure is our liquid level. The property type will be, I guess, you can go for this thing called distance, which is true because liquid level is some sort of distance. We can measure it in meters, and the maximum value of course will be maybe 3. And yeah, our current value is 0.29. So yeah, let's try again. To stop the simulation, just press the stop execution. Then we can run the schedule again. And you can see that the indicator here is literally 0.3. Okay. So yeah, you can see that the tank level is being displayed here. It's still a little bit hard to read, but it's easier to read than this blinking thing going left and right. Of course, your other option is to go for this digital gauge. Okay, and we can use the same tank, we can use the same property, we can do everything the same. Distance, property units, meters, and yeah, and you can even toggle this to display a percentage, meaning to say okay, what it does is it basically takes the current value and it times 100%. So it doesn't mean that you check this display as percentage checkbox. It means that you're literally measuring the percentage. It just multiplies a number by 100%. Alright, so let's do again the last one. You can see that the liquid level height is around 0.3 meters, which is okay. That is what we have. Yeah, and you can see the outflow now is 36,000 kg per hour. So your inflow and outflow is the same. Okay, and the equilibrium, so-called liquid tank height, is 0.3 meters. Right. So what's happening here is that you have this flow going in at about 130,000 pascals, and is pushing liquid into this tank, which will accumulate liquid after some time. All right. Yeah, it will accumulate liquid after some time, and then this liquid height, 0.297291 meters, that will be the height within the tank. And of course all the pressure here will kind of like disappear. I guess it will convert into the kinetic energy in this tank, and then I guess the liquid was just slosh around a little bit after it stops. Okay, this excess pressure is just lost. And the only pressure within this tank is 0.297 meters. So that's 0.297 meters of head, which will give this stream slightly higher than atmospheric pressure. Alright, so this pipe is likely towards the bottom of the tank. Alright, and then the tank is then exposed to atmosphere. Okay, so let me bring paint out, my trusty paint. And this is what the picture is like, if I'm not wrong. So there will be a pipe that is spraying a terminal into a tank. Okay, the tank will be like filled to like what, 0.29 meter. 0.29 meter or 0.3 meter. There is 1 atmosphere of pressure. 1 atmosphere of pressure, and the pipe going out is like so. Then you have your valve here. Oh, that was ugly. Now this is better. And then this one will be exposed to 1 atmosphere. So this is the simulation you're actually seeing. 0.29 meter. So the pressure here equals to 1 atmosphere plus 0.2 or maybe 0.3 meter of terminal. Okay, 0.3 meter of terminal. So maybe you just calculate as a sanity check, what is this pressure, and does this pressure equal to 1 atmosphere here plus 0.3 meter terminal. Okay, I think that should be the rough correct value. Okay, so what's another thing, before I go, what's another thing you must take note of? You must make sure that, well, since this tank here is exposed to atmospheric pressure, MSTR02 must have a flow. The pressure of this flow, the static pressure, should be higher than atmospheric pressure. So this is 130,000 pascals is okay. But what do you notice? You have about 50,000 pascals of pressure drop through this valve. Okay, wow, there's a lot of pressure that's being dropped. Okay, probably the reason why there's so much pressure drop is because there's a lot of flow velocity through this valve. Okay, I guess there's a lot of flow velocity through this valve. That's why that's why there is this a huge pressure drop. Okay, so and there are lots of other details that I'm not covering, but I'll probably leave them to another time. So this is just to help you set up a very basic dynamic simulation and know where to look for your controls. So thanks for watching. I'll see you next time.